Today we're going to discuss motor control in terms of sports performance. It's interesting, the fellow that you see on this slide was my major professor at University of Minnesota, which is where I got my PhD, Dr. Jürgen Konczak. And when I look at this material, I recognize Dr. Konczak. And so there are at least two discrete categories of human movement. First of all, goal-directed movement. And we have been able to identify that the first thing that happens in goal-directed movement is a direction vector signal in the primary motor cortex, and then other neural circuitry are able to control the muscles to achieve that goal to get the end effector, usually the hand, but it could be the foot or the head or a lot of other things, to the point in space where we want it. And the other type of human movement is locomotion. Locomotion may be initiated at the cortical spinal level, but it is dependent upon a lot of subcortical, including spinal neural circuitry, and is characterized by being. So usually in goal-directed movement, the important thing is the trajectory of the end effector. Are we able to get our hand, for instance, to our cup or fork or a pen or a computer keyboard? In sports, the goal-directed movement commonly involves things like throwing a baseball or a softball, a stroke with a racket, a stroke with a golf club, or the kick of the soccer ball, and then a bunch of other variations. So there is a really interesting difference between this type of goal-directed movement and the type that everybody has engaged for centuries. And that is that in most cases, the position is a controlled parameter. That is, getting our hand to the place in space where we want it. However, in sports where we are propelling a ball, the trajectory is actually more important than the position of the end effector. So for instance, if we are pitching a baseball, the important thing is where in the strike zone it crosses the home plate and how fast it's going and perhaps which direction it's going. Nobody really cares about where your hand is when the ball crosses the home plate. And velocity is one of the parameters that is controlled. Now, it's not surprising, and I think all of you have experienced, that the faster you try and move, the less accurate you are. And also that we need interaction torques to recruit sufficient torque within our body in order to get the sufficient speed to the ball hand in overhead pitching, for example, or to the racket head when we are trying to deliver an overhead. So this is something that we've thought about before. Here is an elite pitcher, and the interaction torque starts with his whole body rotating over the lead leg. We're going to talk about pitching in a lot of detail later in the semester. And on top of that, following it by just a little bit, is the flexion and transverse plane rotation of the trunk, followed by the extension, adduction, and internal rotation of the shoulder, followed by and overlapping with the extension of the elbow, finally overlapping and followed by the flexion of the wrist. A very strong biomechanical restraint is vertical ground reaction force in running. In other words, at a given velocity, whether you are running on a resilient track in cushioned shoes or barefooted on the concrete, the vertical ground reaction force remains the same, which is really surprising. But what this reflects is that your body is adjusting to the surface underfoot. For the effective surface lab that we just finished this week, we used to have the students do the activities in the soft sand, on the artificial turf, and on concrete, so 3 conditions. But we found that there was not a big enough difference between the artificial turf and the concrete to actually justify doing it in both conditions. The reason for that is, although there are definitely difference in the amount of force that they're able to absorb, both the concrete and the artificial turf are energy returning surfaces categorically. However, what happens when the surface it becomes soft enough that it's actually a damping surface is an actual change in the behavior of vertical ground reaction force. Now, we have been thinking about how you might use a really damping surface, like the soft sand volleyball court in rehabilitation. And we're going to describe a little bit about how that works. So with an energy returning surface, the surface stiffness is greater than the leg stiffness. So what happens to the EMG output is, first of all, you have an increase for the ankle muscles, which is needed to damp the vibration. However, you get a decrease in the knee and hip muscles, and that is because the lower extremities are able to take maximum advantage of the elastic energy return source of energy, which we have been talking about last week as well. You also have the maximum amount of lower extremity joint flexion. So you have the greatest compression of the linear lower extremity spring, or the greatest bending of all of the lower extremity joint torsional springs. And when you add all the EMG output of all the lower extremity muscles, you have the lowest net EMG. So the lowest amount of energy that needs to be returned in order to do these types of activities like running, jumping, hopping is the least with the energy returning surface. That makes sense, I think, because they are energy returning surface. You don't have to generate as much energy when you're moving on them. A surface could be energy neutral if the surface stiffness is equal to the lower extremity stiffness. That is, the vertical deformation of the leg through all the joints equals the vertical deformation of the surface. If that were true, you'd see a minimum amount of lower extremity joint angle change, but you'd see an increase in lower extremity EMG output relative to the stiff or completely energy returning surface. Of course, whether or not it is a damping surface depends upon the amount of force that a person is generating. For a very big person who's generating a high force, surfaces will be damping on the same surface that might be energy returning for a person with a small body who's creating a low force. This drawing is meant to illustrate what we mean by a damping surface. Here you see a drawing of a foot that is going through the drawing of a surface, that is, that the surface is deforming rather than the lower extremity. So again, with a damping surface, it is the surface that compresses rather than the limb compressing through the bending of the joints against the force. The joints in question include the MTPs, the midfoot, the ankle, the knee, and the hip. The EMG output increases even more because that energy, rather than being returned to the limb, is being absorbed by the surface, and kinematic reversal on phase means that rather than the joints bending as the foot comes in contact with the surface, the joints actually extend into the surface. In this diagram here, we see the effects of a more and more damping surface upon knee angle and EMG. So the top diagram shows the amount of knee flexion with a completely energy returning or completely stiff surface. There we see the knees are bending the most in order to absorb the force the most. And then right at the middle, at what would be an energy neutral surface for that individual, the knee angle is actually not changing at all. As the surface becomes more and more damping, then the knees actually begin to extend. into the surface. But what happens, and this is really interesting, we'll talk about this in the next slide, is that center of mass remains the same. Now over here on the bottom diagram, what you see is that the total net EMG through all the lower extremity muscles is the lowest at the energy returning surface and the highest at the energy absorbing surface, which when you think of surfaces and that way really makes sense. Although the behavior of the lower extremities varies widely in jumping, hopping, or running, depending upon the stiffness of the surface, one thing that remains almost invariant is the vertical excursion of the center of mass. So on a very hard surface, the vertical excursion of the center of the mass will be the same as it is on a very soft surface. The difference will be, as shown on this diagram, a lot of flexion of the joints of the lower extremity when running, hopping, or jumping on a energy returning surface, and very little potential flexion of the joints of the lower extremity when running, hopping, or jumping on a damping surface. This is really interesting and shows the sensitivity of the muscles and joints in response to the stiffness of the surface underfoot in maintaining this almost invariant relationship of the vertical excursion of the center of mass. And here you see in a couple of sentences just what we were describing with that last diagram. I'll give you a minute to read that. Very good. Okay, so what happens in running if we begin to run faster? Does the leg spring stiffness actually not change? That doesn't mean that the excursion of the joints changes. The excursion of the joints will become greater because the force will become greater. And as such, you'd expect that the vertical excursion of the center of mass, since you have more displacement of the lower extremities, would also be greater. However, what happens is the vertical excursion of the center of mass actually. Here is a diagram just to show what's going on. So you see on the picture on the left, if the runner is running slower, you have a greater amplitude of the sinusoidal wave representing the excursion of her center of mass through space, and it has a smaller excursion when she's going faster. But how can this be? Since stiffness is force over displacement, since the force is greater and the stiffness remains the same, then you'd expect that the change in leg length would also be greater. So how can you have less vertical excursion of the center of mass? Okay, this is how it works. What you see is that the faster you go, the more horizontal your legs are, especially at the point when they push off from the ground. So there's more excursion of the leg. It's just more horizontal and less vertical. An important question regarding shoes for exercise and sports training is, do they help or hinder performance? And the answer, like so many other things in physical therapy, is it depends. For example, one might ask the question, do shoes improve or hinder balance? And again, the answer is that it depends upon the fit. So for instance, if shoes have a very intimately fitting heel counter, like you see here, and strong midsole, which links the calcaneus, especially to a broad, flat outsole, then the shoes will actually help improve the balance. If, on the other hand, the shoes are very soft, or the calcaneus is wobbling around within the shoe, then that's actually going to hinder balance. Another thing to think about is the shape of the shoes. Most running shoes have an upturn at the forefoot and toes, such as you see here. And that actually hinders the ability of an athlete to get all the force from all the muscles going through their toes into the ground. And this is why, for doing weight training, wearing shoes that are very flat are actually a really good choice because they allow the athlete to actually get the force from the toes into the ground, such that he or she would not be able to with running shoes like you see in the picture on the left. Remember that the generation of muscular force is a rather slow phenomenon, but sometimes forces are very high, so that the forces being generated by the muscles need to anticipate the forces that they're going to be facing at a kind of a high velocity event like foot strike. So let's think about this together. So what forces need to be stabilized at the foot and ankle? First of all, you have the rotary force in the sagittal plane, which is the external plantar flexion moment on the ankle, and that is managed by the tibialis anterior, the long toe extensors, but when those muscles work, they also cause a posterior translational vector on the foot in the ankle mortise, which is the same direction as the braking force that the foot and ankle are facing at that moment as well. So what do we have to restrain those forces? We have some ligamentous restraints, namely the posterior talotibial ligament and the posterior talofibular ligament, as well as to some extent the lateral retinaculum. However, at least as important as those ligamentous constraints is the compressive force on the talocrural joint. The compressive force is coming from co-contraction of the posterior tibial groups, like the triceps surae, of course, as well as the fibularal muscles and the tibialis posterior. They're contracting at the same time as the anterior tibial group, and so you have compressive forces, high compressive forces, that are stabilizing the talocrural joint as well as preparing the ankle for the ankle rocker against the external dorsiflexion moment or to facilitate control of tibial advancement. Okay, so here we are during the propulsive phase, which is taking place at terminal stance, and we have ground reaction forces that are going in the opposite direction. Remember, as we were saying last week, those ground reaction forces are actually much higher in running than they are in walking. So they are causing an anterior glide of the foot on the ankle, which are opposed by ligamentous restraints, such as the anterior division of the deltoid, the anterior talofibular, and the dorsal talonavicular ligaments. But also by the co-contraction of all those muscles, including the tibialis posterior and the long toe flexors. They have a distal attachment, distal in the foot, and as they pull around the malleoli, they're able to pull backwards. And again, the compressive forces of the triceps surae, all facilitating ankle stabilization. Let's consider the external forces on the knee upon landing. We have a vertical ground reaction force and the braking force, such as we were thinking about in the last few minutes, but the linear momentum coming from the thigh, coming from the femur on top of the bottom, going in the opposite direction of the braking force. And then a gravity of the body, and then finally an external knee flexion moment of tibial advancement. So again, all those need to be stabilized by anticipatory muscle forces because those external forces cause a very high shear force. So what have we got to do that? We've got a contraction of the quadriceps, which is controlling the external knee flexion moment, but at the same time, we've got the highest contraction of the hamstring. So the net result is a really high joint compressive force in the knee, but remember that those joint surfaces actually really thrive upon high joint compressive forces as long as those forces are applied cyclically, which indeed they are during running. Okay, so just to review some of the important ideas of this talk, which was about neuromotor control in the context of sports, remember a really important thing, and I think the most important thing, is that with the possible exception of powerlifting, all sports are taking place at a high velocity. The generation of muscular tension is a rather slow phenomenon, so we really depend upon feed forward or learned motor reaction in order to provide muscular stability to the muscles, because if we were dependent upon online feedback, that muscular generation of tension would be absolutely too slow. Those feed-forward impulses are modified by feedback in order to give us just the right amount of muscular contraction that is most adaptive to the activity that we're trying to accomplish. And remember that ligaments are not just mechanical restraints of joints, they're also sensory organs. So that sensory input of the ligaments really helps the central nervous system to adjust the signals going to the muscles to be able to adjust the tension generated by the muscles to the most adaptive amount. Some locomotion parameters are very strong constraints, which is interesting from the perspective of neuromotor control. But what is really, I think, more important from the perspective in sports rehabilitation is that we can manipulate surfaces, we can manipulate shoes in order to accomplish the right effect at the right point.